is lesson 9.6, powers of monomials. You can use the property for finding the product of powers to find a property for finding the power of a power. For example, if we have 5 to the third to the fourth, we can use what we know of exponents to expand this whole thing, and we'll use 5 to the third as a factor 4 times. So we'll have 5 to the third times 5 to the third times 5 to the third times 5 to the third. And then we already know when we multiply things with the same base, we just add the exponents. So this would be 5 to the 3 plus 3 plus 3 plus 3, or 5 to the 12. Notice the shortcut here to get this 12 is to multiply 3 times 4. So that gives us this power of a power property. To find the power of a power, multiply the exponents. So we have one power raised to another power, we multiply the two exponents. Alright, so let's apply that property to these first few examples. Simplify each one. So 4 to the third to the 7th. We will multiply the two exponents, and we end up with 4 to the 3 times 7 is 21. Here we multiply the two exponents, we have n to the 4 times 4 is 16. And now with this one, remember with negative exponents, the first thing we have to do is rewrite this as a fraction with positive exponents. So we'll first change this to 1 over 2 to the third squared. And now we can use our power of a power property. And we'll multiply the two exponents here to get 1 over 2 to the 3 times 2, which is 6. Okay, so there's a couple for you to try on your own, so pause the video and work through those three, and when you're ready to check your answers, press play. Okay, here you should have gotten 12 to the 6th. This is f to the 35th. And this one is 1 over t to the 8th. Or you could also, remember, you can write these with negative exponents. So this could also just be t to the negative 8. And notice that's what you get if you went ahead and multiplied these before rewriting it as a fraction. I jumped right to that in this one, but you can multiply the two exponents first before you rewrite it. Okay. The power of a power property can be extended to find the power of a product. So for example, if we have 3d squared to the third, again we'll write that out using what we know of exponents. So this means we'll use 3d squared as a factor 3 times. So 3d squared times 3d squared times 3d squared. Okay. And we see here that we have 3 multiplied 3 times, so this is 3 to the third. And we have d squared multiplied 3 times, so this is d squared to the third. And then using our power of a power property that we just learned, we know that we can multiply these exponents. So this is 3 to the third, d to the 6th. And notice here, the way that we would get this without actually having to write this out is basically, it's not really using the distributive property, but it's kind of like distributing this exponent to each of the things in the parentheses. So 3 gets raised to the third power, 3 to the third, and d squared gets raised to the third power. D squared to the third is d to the 6th. So that's the shortcut or the property that allows us to do that. So the power of a product property says to find the power of a product, find the power of each factor, and multiply. So for example, if we had ab to the power m, that would be a to the m, b to the m. Okay, so let's try that with a couple of examples. So for 2a, we have 6w to the 4th, all to the 5th. So we want both of those to be raised to the 5th power. So it's 6 to the 5th, and w to the 4th to the 5th. And here's again where we multiply those exponents. So w to the 20th. Okay. Same thing here. In this case, we have 1, 2, 3 different things in the parentheses. So all 3 of them need to get this exponent of 3 on the outside. So here we have negative 4 to the 3rd. And then s to the 5th to the 3rd. So we'll multiply the 2 exponents and get s to the 15th. And then t to the 7th to the 3rd. So we'll multiply the 2 exponents there and get t to the 21st. And then we could actually go ahead and multiply this out. This is negative 4 times negative 4 times negative 4. So it's negative 64. S to the 15th, t to the 21st. Okay, one more. So again, we'll make sure that each of the things in the parentheses gets this exponent on the outside. So here we have 3 squared. And then x to the negative 2 squared. So when we multiply these 2 exponents, we get x to the negative 4. And then y to the 4th squared. So when we multiply those 2 exponents, we get y to the 8th. Alright, so let's go ahead and take care of this right here. 3 squared we know is 9. And again, you could leave this with the negative exponent, or you could write this one as a fraction. So we'd have 9 y to the 8th over x to the 4th. Either of these are perfectly okay. Okay, so the try it yourself problems for this example are on the back of the page at the top. So go ahead and pause the video, work through those 2 problems, and when you're ready to check your answer, press play. Okay, here you should have 6, wow, not what I wanted. You should have 16 b to the 24th. And then here we should get 25 a to the 6th, b to the 8th. Okay, let's look at a couple examples that involve some geometry. Example 3 says, find the area of a square with sides of length 7, a to the 8th, b squared. Well, if you check your formula chart, or look in the back of the book where the formulas are, you'll find that the area of a square is a equals s squared. We want to find the area of a square with sides of length 7, a to the 8th, b squared. So we'll take this expression, and since that's the length of the side, we'll replace the s in the formula with 7, a to the 8th, b squared. So we have 7, a to the 8th, b squared. Okay, so now this looks like the same types of problems, the same types of expressions we've been simplifying already. So we'll make sure everything in the parentheses gets squared. We'll end up with 7 squared, and then a to the 8th squared, so a to the 8 times 2 is 16, and then b to the 2nd squared, b squared squared, so 2 times 2 is 4. But of course we can write 7 squared a little bit more simply, so we'll go ahead and write that as 49, a to the 16th, b to the 4th. And one more example for this section. This one says the radius of a grain of pollen from a certain flower is 2.5 times 10 to the negative 3rd millimeters. Use the formula V equals 4/3 times 3.14 times r cubed to find the volume of the pollen. Express your answer in scientific notation rounded to the nearest hundredth. Okay, so we're going to use this formula. V equals 4/3 times 3.14 times r to the 3rd. So we want to find the volume of the pollen. We know the radius, r, is 2.5 times 10 to the negative 3. So let's replace the r in the formula with 2.5 times 10 to the negative 3rd. Notice in the formula this is r cubed, so we have the radius cubed. Okay. Well now, in order to get a nice good number here, we're going to first need to distribute this exponent. And if you prefer, you actually could do a fair amount of this in the calculator, especially this portion with the scientific notation. If you do it by hand, though, we want to make sure that both of these get distributed. So we'd have 4/3 times 3.14 times 2.5 to the third, and then times 10 to the, this would be -9. Okay. And because we want our answer in scientific notation, here's our power of 10. What we really want to do is just take the numbers and multiply them. Let's go ahead and multiply those. We want 4/3 times 3.14 times 2.5 to the third. So we'll do the 2.5 to the third first, and then multiply by 3.14, and then multiply by 4/3. So since these are all over 1, we're multiplying by 4, and then divide by 3. Since we want it rounded to the nearest hundredth, we can go ahead and divide. And that should come out to 65.416 with the 6 repeating. Okay. Alright, now this sounds pretty good, except when you look at this factor here that's multiplied by 10 to the -9th, this is not between 1 and 10. So what we actually need to do is move the decimal back one spot so that we have 6.54, since that's rounded to the nearest hundredth, times 10 to the... Alright, now this might be a little tricky to figure out what happens to this exponent. Think about it this way. If I wanted to write this number in standard form, since this is a -9, this is a very, very small number, I'd move the decimal back way, way, way over here. Well, I moved the decimal back one spot, just one spot, and now it's closer to 0. So this exponent should also be closer to 0. So it's 6.54 times 10 to the -8 millimeters. Okay. And don't get too lost in the scientific notation here and just the way this was all calculated. There are several different ways to get from this step right here down to this step right here. You could, again, do a fair amount of this in the calculator, so don't get too confused between right here and right here. If there's another way that you can get the same answer that's mathematically equivalent, that's perfectly fine. This is just one possible way to look at this. The main thing is that you can substitute the radius in place for r, and you can do something with that. Okay, so there are 2 try-it-yourself problems. So go ahead and pause the video, work through those 2 problems, and when you're ready to check your answers, go ahead and hit play. Okay, for the first one, the area is 81 x to the 6 y to the 10. And for the last one, the surface area in scientific notation is 2.826 times 10 to the -7th millimeters. Okay, let's take a look at lesson 9.7, linear and nonlinear functions. So recall from lesson 8.3 that linear functions have constant rates of change and have graphs that are straight lines. So then it should make sense that non-linear functions are functions that do not have constant rates of change, therefore their graphs are not straight lines. So this is one way that you can identify something that is non-linear. The graph is not a straight line, it is non-linear. So for example 1, determine whether each graph represents a linear or non-linear function. Explain. Well, for the first one, we look at this graph and we see that it curves right in the middle. This is not a straight line, so we would say that it is non-linear. And for our explanation, we would say the graph is not a straight line. Okay, and for B, this is a straight line, so this function is linear. And again, our explanation is because the graph is a straight line. Okay, so for the next two, the try it yourself problems, pause the video, answer those two, determine whether each one is linear or non-linear, and then press play to check your answers. Okay, for these two, the first one is linear, the second one is non-linear. Okay, well, we won't always have a graph of whatever function we're dealing with. So it's helpful to know how to tell if it's linear, if a function is linear or not, in other ways as well. So recall from chapter 8 that the equation for a linear function can be written in the form y equals mx plus b, where m represents the constant rate of change, or the slope. Therefore, you can determine whether a function is linear from its equation. If it's linear, it would have to be either already written in this form or able to be transformed so that it could be written in this form. So let's take a look at some examples. The first one, y equals 1/5 x. Well, this looks a little bit like y equals mx plus b. Let's look at it pretty closely. We start off with y equals. Yep. We have a number times x. 1/5 times x. Yep. The only thing we're missing is the plus b, but if you remember, we did actually see a few equations like this when we dealt with linear functions, because I could just put a plus 0 at the end of this, and now I have y equals mx plus b, and I haven't changed anything at all about the identity of this function. So this one is linear. It is already pretty much in the form y equals mx plus b. Let's look at this one. We have y equals 2 to the x. Well, this x is in the exponent. It's not down here like this. And there's no way that we're going to be able to get that x out of the exponent, at least not with what we know as of right now. So this one is definitely non-linear. Okay. And the last one, x plus 3y equals 9. Well, again, it's not in this form, y equals mx plus b, but we could start to try to get it in that form to see if that's possible. So if I want it to be y equals mx plus b, it needs to be solved for y. So we want to try to isolate the y. Well, the first thing I would do would be to try to get rid of this x by subtracting. So we'd have 3y equals, and since we want it to look like mx plus b, we'll put the term with the x first. So minus x plus 9. Okay, and from here, you may not actually need to finish the complete next step, because you might be able to see that just by dividing everything by 3, that will put that in slope-intercept form. But if we need to, we'll go ahead and divide everything by 3, so that we can now see what that looks like. We know there's an imaginary 1 in front of this x, so this is negative 1/3 x plus 9 over 3, which is 3. And this is definitely in slope-intercept form, so this is linear. And as far as the explanations go on these, the ones that are linear, either are already written in slope-intercept form or could be written in slope-intercept form. The one that's nonlinear, however, could not be written in the form y equals mx plus b. That is the one thing that makes that not a linear function. Okay, so there's some try-it-yourself problems for you to do on your own. Pause the video, work through those 3 problems, and when you're ready to check your answers, press play. Okay, the first one is linear. The second one is nonlinear. And the last one is also nonlinear. Okay. When we're looking at a table to determine whether a table represents a linear or nonlinear function, you will want to remember that a linear function has a constant rate of change. So we should be able to see that in the table. So here we see that x is increasing by 1 each time. And then y, from negative 5 to negative 20, goes down 15. But then from negative 20 to negative 45, goes down 25. And then from negative 45 to 80, that goes down 35. So there's definitely a pattern here, but the change is not constant. So this would be a nonlinear function, because this rate of change shown in the table is not constant. Well, let's take a look at B. Here, the x is increasing by 3 each time. And then y from 10 to 14 goes up 4, 14 to 18 goes up 4, and 18 to 22 also goes up 4. So then we see that this has a constant rate of change all the way through the table. As the x values increase by 3, the y values increase by 4. So that means that this one would be linear. Okay. There are 2 more problems for you to try on your own. Pause the video, determine whether each of those tables is linear or nonlinear, and then when you're ready to check your answer, press play. Okay, the first one is linear, and the second one is nonlinear.